Hello, and welcome to this PowerFilm and CAP-XX webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today is Sam Jones. Sam is an R&D engineer at PowerFilm Solar. Also with us today is Jeff Colton. Jeff is the Executive Vice President at CAP-XX. And with that, I'd like to pass things along to you to get us started. So gentlemen, go right ahead.
Thanks, Katie. Like Katie said, I'm an engineer here at PowerFilm Solar. I've been with the company for about 7 years, working on a lot of different projects, mainly in the IoT space. A little bit of background on our company. We design and manufacture custom solar cells, modules, panels, power solutions for a number of different sectors, one of those being IoT, but we also provide solutions for transportation, military, consumer markets. We use a proprietary thin film material, but we also use higher efficiency cells when that makes sense. We're located in Ames, Iowa. We have one facility, so all of our design and manufacturing, material fabrication is all done in the U.S. So before we jump into things, it's good to kind of understand what problem we're trying to solve. And most of the problems that energy harvesting solves is really related to the battery. So either you're not getting long enough battery life for your use case, you have limited power due to that finite capacity, so you're forced to cut those critical features or reduce the functionality of your device to get that extended battery life that you require. And then battery bulk is really huge for wearables or portable electronics, where reducing the bulk volume is really critical to a lot of innovative use cases. And battery volume can take up a very large percentage of the actual space of a wearable or low power electronic. So how does energy harvesting solve that problem? Obviously, if you have a continuous perpetual source of energy, you can extend that battery life sometimes indefinitely. You can expand the functionality of your device. You can add back those critical features and what I like to call power resilience. So you can overcome some of those that unknown aspect of the real world where things that you may not have predicted could occur. Maybe you have to push a couple extra firmware updates to your device. Maybe your device loses connection more often than you anticipated. All those things have an impact on power, and having an energy harvesting solution can make you resilient to those unknown elements. And then some of these innovative form factors, such as our thin film flexible PV material, can really enable those compact low profile electronics that are going to be required for the next generation of wearables and portable electronics. So what sort of sensors and devices are compatible with energy harvesting? I sort of threw this slide up to give you a really broad context. When you talk about ultra low power, you've got things like temperature, humidity, air quality, soil moisture, even things like GPS and cellular devices like the newer NB-IoT and LTE-M protocols. Even just a couple years ago, a cellular device, you would not characterize that as ultra low power. But with these newer protocols, you have more control to really control the power consumption. So you could, if you set up a device that only sends data once a day, you could power that device with something a PV cell the size of a quarter. In the middle here, we got low power electronics, so things like GPS, NB-IoT, LTE-M. If you're pinging those things more frequently, they're going to consume more power. Health monitors, smart locks, accelerometers, acoustic sensors. Then you have mid to high power devices, and those may take more solar. You might need a tablet size or larger. GPS, those cellular devices, if you're pinging them really frequently, every couple seconds. Wireless gateways and controllers, cameras, drones, large actuators, lights, all those things require a little bit more power. So you can kind of see in general, any device that you would think of as running on a battery could potentially be a good fit for energy harvesting, and you could get a lot of benefit from a energy harvesting solar solution. So what are the components of an energy harvesting system? There's a couple key components. In the middle here, you got the power management IC, or a PMIC. This really controls where the energy flows between the different devices. So you have energy that's generated from the harvesting element, whether that's a PV cell or a thermoelectric or a piezoelectric or RF antenna, and that energy flows to the storage element. So you could have a lithium polymer battery, or what we're going to focus on today is a super cap solution. You could have a standard cap, solid state nickel metal hydride, and then a lot of times this PMIC has built-in features that can offer load management or load prioritization. So it can really optimize and utilize energy in an efficient way. So looking specifically to PV harvesting with a solar cell, a lot of times we're looking at different spectrums, different environments. So a good way to kind of differentiate and understand the difference between the different light sources is to say, what's the difference between indoor and outdoor light? So in an outdoor space, that's easy because solar in general is optimized for a solar spectrum. So your solar panel is going to come rated with a output at 1,000 watts per meter squared, AM 1.5. And you could go to NREL's website and you could type in your location and you'll get an estimate of how much irradiance you have in that area. So calculating how much energy you're going to get out of a PV panel for an outdoor use case is usually pretty easy. When you move to indoors, these things are not as easy. And that's because in an indoor space, light intensity is measured with lux. And lux is not like irradiance. Lux is a measure of brightness, which I'll talk about in the next slide, and it really depends on spectrum. So it's not as easy of a direct correlation. Lux is used as a measure of brightness for indoor environments, so it's important to understand what lux is and how it affects the performance of a PV panel. And the definition of lux is that it's a measure of brightness as perceived by the human eye. So if you see the curves on the right here, green light is the most efficient. So it requires the least amount of energy to appear the most bright to your eye. And if you compare that to red light or blue light, those light sources require more energy. They have to contain more energy to appear the same amount of brightness to your eye. And that affects, so the color of the light affects how a panel will perform, because a panel really cares more about how much energy is present in that spectrum than it cares about the color. So in general, a rule of thumb is that for the same lux value, so say we're talking about 200 lux indoor, a warmer colored light spectrum will have a higher power density or energy density than a cooler spectrum. So a warm white LED will have more energy, will contain more energy than a cool white LED. And that usually means that the PV cell will generate more power under a warmer light source than a cooler light source. So if you understand lux, so lux is going to be, the light is going to contain different amounts of energy for different spectrums. You can use lux to define light intensity. And really, light intensity is what the PV panel cares about. And you can see this graph here plots light intensity in outdoors all the way down to indoors. You can see that power generation scales linearly with light intensity, and that there's a very, very large difference between the light intensity of direct sunlight versus the light intensity indoors, say on a desktop. It could be 1,000 times less intense. And that really means two things. One is that it means that the power that is generated by a PV cell is 1,000 times less on a desktop than it is under direct sunlight. And then 2, it means that minute material defects that are inside that PV material that would not normally affect direct performance under direct sunlight are going to become more and more prevalent as you reduce that light level. So when you start getting below, say, 10,000 lux, some of these smaller defects start to really pull down the performance of a panel. And it can really quickly pull the output to 0. So you really want to make sure, and I'll go over this in a couple slides, of you want to source panels that are rated for the light intensity. You wouldn't want to use a panel that's rated for direct sunlight and then use it or expect it to perform well on a desktop. So then how does light spectrum affect PV performance? Well, PV material absorbs differently under different spectrums. And panels that are optimized for a solar spectrum, they may not perform well or may not perform at all under different spectrums when you remove some of those components that technology was optimized to absorb. This is kind of displayed in these graphs here, where you can see amorphous silicon versus monocrystalline silicon versus triple junction gallium arsenide. Under an outdoor solar spectrum, amorphous silicon has the lowest efficiency. But when you bring it in under an LED spectrum, the amorphous silicon has the highest efficiency. That's just because when you start removing those infrared and UV portions of the spectrum, those 2 higher efficiency solutions, they don't perform as well. Another really important consideration is how you construct the cell mechanically. So how many cells, and electrically. So how many cells do you have in series or parallel, and how does that match up with the conditions of your environment? A lot of times for energy harvesting and portable power and wearables, we run into a lot of really irregular shading and lighting conditions. So a lot of times we use single cell PV modules to overcome those awkward shading patterns. So this phenomena is caused by Kirchhoff's current law. If you block light from one cell, you're essentially not allowing current to flow through the whole panel. Whereas a single cell PV, if you cover half the cell, current is still able to flow in the other half. It's kind of like a water pipe, where if you cover half the water pipe, or if you block half the water pipe, water is still able to flow through the other half. So we really recommend using fewer cells or larger cells when you're in an indoor environment, or if you're in an environment where you may expect awkward or very irregular shading patterns. And that can be caused by a lot of things, and especially we run into that a lot with our flexible material, where many of our customers are taking advantage of that flexure and wrapping around curved surfaces, and that really can inherently induce these shading patterns. So how do you choose the right PV cell? Based on the slides above, you want to find a cell that's rated for your target light intensity. You want to find a cell that's rated for your target light spectrum. So you want to source a cell that's going to perform under the expected shading and lighting conditions. So if you're installed permanently and you're expecting direct sunlight, maybe you don't really care. You can have more cells in series, but if you are expecting irregular lighting patterns, you definitely want to opt for a single cell design. And then you want to find a cell that's rated for your expected environment: UV, moisture, impact, abrasion, flexure, temperature. All these things, a cell needs to be able to be resistant and tolerant to whatever environment it's going to be exposed to. So energy harvesting power management ICs, like I said, are the brains. They're the middle. They connect all the things, all the pieces together. So there's a list of what I call critical features. But really, the critical features for the PMIC are really use case specific. A lot of PMICs have different function or features, and you may find a feature that enables a critical feature of your application. My example on the right here is our joint development kit with EPs using their AEM 10941 PMIC. It's a great PMIC, has a good efficiency, lots of features, very widely versatile, applicable for lots of different applications. It also has the CAP-XX footprints on the backside. So if you're really interested in taking next steps with energy harvesting with supercaps, I'd really encourage you to utilize this development kit. But some of what I would say are common critical features for PMICs are over and under voltage protection. So making sure the PMIC will stop charge your storage element appropriately and protect it on both the top end and bottom end. Low voltage input. So that's really critical for those wearable and portable electronics where you're trying to boost a low voltage single PV cell up to charge, say, a battery or take full advantage of your supercap voltage range. And then also really critical for batteryless applications using a supercap is what's called cold start. So being able to charge efficiently from system 0 volts to when that PMIC can turn on its normal charging algorithm, which is usually around 1.5 volts. Some PMICs have really great cold start algorithms. Some don't support cold start at all. Some have really poor performance. So if you're looking at a batteryless application, you definitely want to understand the cold start functionality of your PMIC. Then there's a lot of different bonus features, or what I call bonus features, and maybe this is a critical feature for your application. Things like primary battery backup, DC-DC or LDO supplies, supercap balancing. So that could be really critical for a lot of you who are listening today. Load or storage prioritization. So maybe you don't want to wait to charge up your supercap fully before you want to start powering your load and maybe pinging your Bluetooth signal. Power metering is a really cool feature that some PMICs have integrated in. Being able to see the power that's being generated by your PV cell in live time. Programmable interfaces such as I2C, and then efficiency. So a lot of PMICs have really great efficiency over a wide range of input voltages between 85 and 95%. And then there's other considerations that are sort of standard for any electronic. How much footprint does it take up on your PCB? How many external components does it need? And then how much additional cost does that add to your BOM? And then my final slide, well, my second to final slide, is really to optimize your load. So a key theme of energy harvesting is that all the pieces need to work together to create a solution that works. And part of that is really scrutinizing the power consumption of your load. If your load is not optimized for low power or the lowest power that it could be, finding an energy harvesting solution that works is going to be very difficult. My plot here kind of demonstrates how energy consumption of a Bluetooth device is linearly related in an exponential way to the data rate. So a standard Bluetooth data rate could be anywhere from 10 milliseconds to 100 milliseconds. But in this regime, that's considered high power. Setting that transmission interval to be much longer in the 1 second range can have an exponential impact on your device power consumption. So really looking at those things like, am I taking advantage of deep sleep appropriately? Am I setting my data rate that matches my use case? Am I using a transmission power that makes sense? Passives, log, am I disabling logs? Am I disabling unused features? Am I configuring my system to maximize power efficiency? We've done a lot of work with Nordic ICs, and they are really built from the ground up for low power. So then they have a lot of great tools for optimizing power consumption for both Bluetooth devices and their new cellular line. So if you go online, they have a really neat calculator for typing in your different cellular parameters, and then they can give you an estimate of what that power consumption will be. And then finally, if you want to get started with energy harvesting with PV cells and super caps, we have a lot of standard products, and like I said, we have a development kit. I know CAP-XX would love to send you samples. We have a Horizon blog. We call it the Horizon blog, but it's really a technical blog that's aimed to answer a lot of common questions we get from people in the IoT space and about energy harvesting and remote power. We have a custom design tool for our thin film technology. So if you can't find a design that fits your dimensional or power requirements specifically, you could go on and see how you can change dimensions or the number of cells to get a specific voltage or current or dimensions. And then finally, if you have an application that you want to see if energy harvesting is a good fit, I'd encourage you to reach out and contact us. We'd love to work with you. With that, I can pass things on to Jeff, and he can tell you more about how you really can achieve a batteryless and ditch that battery and take advantage of super caps for IoT applications. Thanks.
Thanks, Sam. Jeff here. So my name's Jeff. I'm with CAP-XX. I've been in the energy storage business for about 30 years. I'll give a quick overview of CAP-XX. CAP-XX was founded in 2000, so been around over 20 years. We're located in Sydney, Australia, with worldwide operations, and we're publicly traded on the LSE under CPX. We follow a dual market strategy of IP licensing and direct product sales. Our claim to fame is we make the world's thinnest, highest power with low leakage current super caps. In Sydney, we have best-in-class engineering and supercapacitor component integration support. Our team has been there a long time, hundreds of customers, hundreds of applications, and they're really experienced and really knowledgeable about how to make supercaps work in your application. CAP-XX supercap technology is licensed by many other companies that manufacture supercaps. Examples are AVX, Murata, TDK, and CDE. They all license CAP-XX technology to produce some supercaps. And about a year ago, we acquired the Murata supercapacitor business. So we had licensed our technology to Murata and then entered into an agreement with Murata where we acquired their entire supercap business. We picked up all their manufacturing equipment and moved it from Japan to Australia. And so now we have manufacturing in Australia, Malaysia, and China. What are the unique characteristics of a supercap? And that is that differentiates them from batteries. One is that they can deliver huge amounts of power very quickly, and they can also absorb huge amounts of power very quickly. They can be charged and discharged fully in a second or less. So if you compare them to a lithium coin cell, it's 2,000 times the power capability of a lithium coin cell. Or if you were to compare them to a electrolytic capacitor, it's 639 times the amount of energy that you could store in an electrolytic capacitor. So a supercap is kind of a cousin to a standard electrolytic capacitor or film capacitor or other type capacitor and a battery, and it kind of fits right in the middle. It stores a good amount of energy, but can also deliver that energy in very, very rapidly. They have a great life. They can be charged and discharged 1 million times, 1 million charge-discharge cycles, whereas a battery might be 10,000 or 20,000 charge-discharge cycles. And that's a lot for a battery. And most of the time we design for a 10-year life cycle, but we could design for a 20-year life cycle or less, whatever your design criteria is. We could design that supercap that fits the life requirement of the application. They operate -40 to 85 degrees C, which is a significant deviation from batteries. Battery starts to not perform well in cold temperatures. They use an electrochemical reaction, and that electrochemical reaction is usually inhibited by cold temperatures. Supercaps are an electrostatic device, so it's actually almost no impact at all to have cold temperatures, no impact at all on the internal resistance or the amount of power that can be pulled out of the device. So easily down to -40 degrees C and up to 85 degrees C. Supercaps are highly charge efficient because it's electrostatic, because you don't have to drive an electrochemical reaction. Energy flows in and out very easily. And these are ideal for micro-harvesting applications because for every amp you put in, you get 0.99 amps back out. As opposed to battery, for every amp you put in, you might get 0.8 amps back out. So you lose a lot of energy in trying to drive that electrochemical reaction. So in terms of discharge rate, if you're familiar with the C rate of a battery, you might have a 10 C rate, 10 times the rated capacity, rated amperage of a battery. A supercap, if you were to rate it the same way, you don't, but if you were to use the same terminology for a supercap, they would be able to be discharged at 1,000 C rate, orders of magnitude greater discharge rate, charge and discharge capability. And we make supercaps as thin as 0.4 millimeters, which is less than half the thickness of a credit card. And also the constituents or components inside of a supercap are non-hazardous. We make 3 main product lines. On the left side of the screen, you'll see our Prismatics, and that was the 0.4 millimeter product I just discussed. These products are used for space-constrained applications. You have to have a thin, if you have a thin device like a wearable, a watch, some type of device that is very space-constrained, then these super thin, ultra-thin supercaps might enable the application. And this slide I picked up right from our website. So if you were to go to our homepage on our website, you can scroll down a bit. You'll see this exact same side. You just click on the category of product that you just want, and boom, you're into the meat of the product. The second, or the center picture shows your standard pan-based supercaps. Those are when cost is the primary driver and you're not space constrained. So we make hundreds of these, just different types of products available in various voltages, typically 2.7 volts for a single cell, 5 or 5.5 volts for a dual cell assembly, and we provide, whatever your requirement is, we have probably a supercap that'll meet that. And then on the far right side are the large supercaps. The one pictured is about the size of a Pepsi can, and it's 60 millimeters in diameter, 3,000 farad, so it's a huge supercap. Those are generally used for microgrid harvest or microgrid applications, not electronic applications. A little bit about the Prismatic line. You can see here pictures of, on the left-hand side, the Prismatic supercap, very flat. So those are the products we picked up from Murata when we acquired the Murata supercap business. The center page of the CAP-XX legacy products that have been in production about 10 years. And the third picture to the right is a good picture because you can see that that's a dual cell. If you look on the left-hand edge of that, you can see that there's actually two cells together there. So that's a 5-volt cell, because it's got two 2.7-volt cells assembled together. And a supercap operates generally at 2.7 volts. We do have 3-volt cells, and we also sometimes operate them at 2.5 volts or 2.3 volts. And that's a strategy that you can use to extend the life of the product. If you wanted a 20-year life, you might operate it at 2.5 volts instead of 2.7 volts, and you could extend the life that way. We make 45 different prismatics, and both in single and dual cell configurations. And occasionally we have a customer that needs a higher voltage than 5 volts. And we can assemble however many cells you needed to achieve your voltage requirement. Again, in the table you see, this is clipped right from the website, and you can see that when you go to the website, you can go to a table. You can select by voltage. Customers almost always know what voltage they need, and they sometimes need help sizing the application, and we can provide that. But so the first criteria is what operating temperature do you need, then what voltage do you need, and then how much capacitance do you need. And then if you'd like to, you could just get samples right off our website. So boom, you get the sample and we ship them within a week. This is a similar idea here for the cylindricals. There's a lot more cylindricals, and again, these cylindricals are used where you don't have a space-constrained application. The prismatic might be 2 millimeters in thickness, and the minimum here I think is 8 millimeters in height. So it's much larger, but also they're much less expensive. This is a cost, this is a cost play here. You're not space-constrained. Cost is the driver, and so these cylindrical cells are, somewhat of a commodity, and many manufacturers of these. This is an example of a meter, smart meter, an Itron smart meter that we're in. This is on our website here. So I put this slide here to show you how to navigate and pull information from the website. So if you look at the I think it's the 6th one from the left. It's a smart meter icon there. If you click on that smart meter icon right up our homepage, you'll pull up this use case, and it goes into the details of how do you use supercaps in a smart meter application, and it also how do you use energy harvesting in a smart meter application. It goes into a very detailed description of the supercaps and smart meters. And it also provides a whole bunch of white papers and supporting documentation about the implementation of supercaps in the application. And so there's 8 different applications that we're showing on this website with it, and it's formatted. Each application is formatted the same way. So you've got white papers, application briefs, cell balancing, all kinds of supporting information to help you design in the supercap into the application. And if you would like to have support from CAP-XX in the design process, we have an application worksheet that's got, I think, 20 questions in here. They're drop-down menus, so it's real quick to fill out. This is available on the homepage of our website. You just download it and shoot it to us. But what operating voltage are you in parallel with a battery? Questions like that. And then in the lower left-hand corner, a lot of customers want to know how long is the supercap going to last in the application, and that's driven by time at voltage and time at temperature. So how much time will it be at 85 degrees C? At 2.7 volts, and if you can just estimate those things, we have a very sophisticated model that's been developed over 20 years that will produce a estimate about how long that supercap is going to last in that particular application. One additional point is that the failure mode of supercaps, again, or the aging mode of supercaps is time at temperature and time at voltage. So if you drive a supercap 2.7 volts or 2.8 volts at high temperatures, they age more quickly. If you look at the data sheet and it says 1 million charge-discharge cycles or 20-year life, that's based on 25 degrees C, 2.7 volts. So your application might not be 2.7 volts and 25 degrees C. So if it's not, and you want to know, you want to really customize the data sheet to your application, this is a tool that allows us to do that for you. And so you just download it, fill it out, and shoot it back to us, and our applications engineers turn these around all day long, and love to do it for you. And that concludes the presentation. Now, actually, one more slide here. We do have a 3-volt cell that's in development, and we basically got this 3-volt cell at the sampling stage. We are interested in a high-volume beta customer that will help justify the launch of the product, but it will help eliminate maybe an LDO or a buck boost converter. So the 3-volt might pair perfectly with someone using a 3-volt lithium cell or putting 2 3-volts together, a 6-volt application. So if you're interested in a 3-volt supercap, we're very interested in talking to you about that also. And then finally, this is a final slide here. It's got my contact information at the bottom. Website is CAP-XX.com. And again, there's all the specific applications, asset tracking, automotive applications. A huge application for us is electronic door locks, medical devices. We've got several examples of medical devices on the website, PDAs and point-of-sale devices, smart meters, wearables, smartwatches, and wireless sensors. There's several examples of wireless sensors on the website too, actual wireless sensors that we're in. Katie, that concludes the presentation. We'd love to take any questions now.
Okay, Sam and Jeff, thank you both so much for that great presentation. We do have questions that have come in from our attendees, and we are going to move into answering those right now. So, gentlemen, our first question today. Supercaps are great for fast recovery. How do they handle trickle charging?
They're fabulous for trickle charging because they're so efficient. So trickle charging is basically what's happening when you're charging a supercap from a micro energy harvesting device. And they're very efficient. There's very little losses in the charging process. And so they're the go-to energy storage product for trickle charging for micro energy harvesting applications. They work great in trickle charging applications.
Okay, thank you so much for that answer. Another question here. Can you quote a value for power leakage? I think that's probably a supercap question, and it depends on the supercap, prismatic or cylindrical, what size it is. So no, I can't really quote a value off the top of my head. I need more details to answer the question. Okay, thank you so much. We will get back to that attendee following the webinar with some more information for you. So, gentlemen, another one here. The IoT device we have uses CR2450. To start looking for a solution, we would need to do an application worksheet.
Or give me a call. The application worksheet is a tool there available, and it's actually a great tool to have discussions from. So if you wanted to do the application worksheet, great. Or if you just want to send me an email or give me a call, I'm happy to talk from the information that you provide.
Okay, thank you so much. A reminder to our attendees, if you do have a question today, place it in the Q&A window and click Submit. We will do our best to get through as many as we can. So next one here, gentlemen. What is the best way to connect to a PV cell electrically?
I think this one's for me. There's a lot of different ways you can connect, and it really depends on your specific use case or your enclosure, what your mechanical setup is like, and also what sort of volume you're looking at driving. If you're in a 100-unit production or beta production, maybe it makes sense to just solder some leads on and go that route. If you're talking about tens of thousands or hundreds of thousands of pieces, then maybe opting for some sort of connectorization or surface mounting the PV cell to a PC board or something like that may be a great choice for you. There's a lot of different ways that you can do it. So if you are curious, just reach out to us and we can help work through that aspect of the application.
Okay, Sam, thank you so much. Next one here, gentlemen. Can supercaps be paralleled for larger current applications and still retain all of the same features as a single supercap?
Yes, they can. So, when you parallel or series a supercap, when you parallel the supercap, you maintain the voltage rating of the single cell. So if you were to take two supercaps and parallel them, you'd end up with 2.7 volts and double the capacitance of the two caps that were paralleled. If you series them, you add the voltage. So if you were to put two supercaps in series, you go to 2.7, so a 5.4 volt series, two-cell series is 5.4 volts, but you have to half, then you cut the capacitance in half. If you had a 1 farad, two 1 farad supercaps that were series, you'd end up with a 5.4 volt supercap at half a farad, 0.5 farads. And, you can do this. We've got one application, I think, that series puts 14 in series in order to get 14 times 2.7. We often have multiple applications that have multiple parallel strings, so 3 or 4 or 5 or however many parallel strings you need. So supercaps kind of a building block. They're used as building blocks, very similar to batteries. There's some unique rules like halving the capacitance, but they're often, almost always they're in series and they're in some kind of series and parallel configuration.
Okay, Jeff, thank you so much for that answer. Another one here, gentlemen. Can you design solar cells in custom shapes and sizes?
I think that one's directed for me. Short answer is yes. The way that we manufacture our material is all roll-to-roll on a plastic substrate, and it goes through various deposition processes and screen prints and laser scribing to define the features and the size and the shape. And all that's very customizable with certain specific limitations. Certainly, any rectangular size from 1 by 1 centimeter all the way up to maybe, let's say, 20 by 20 centimeters is very, very simple, very easy for us to do. We could also do pretty simple shapes like circles. But yeah, if you have a unique, funky shape or design, we'd love to work with you and see if we can provide that. Oftentimes is one of our biggest value adds is that we can do very unique, innovative designs that meet the dimensional mechanical requirements of your application specifically.
All right, Sam, thank you so much for that answer. A reminder to our attendees, if you have that question, enter it into the Q&A window and click Submit. We will do our best to get through as many questions as we can. Next question here, gentlemen. just a comment and a question. This person is saying, great talk from you both, thank you. And then he is asking, can either speaker comment on best practices and or performance in applications using hybrid storage solutions? An example, Supercap and secondary cell, etc.
Sure, Jeff here. So supercaps are often paralleled with batteries, and we have a lot of content on the website about how to do that. But often the main driver is to use in order to reduce the size of the battery or use a battery technology that's got great energy capability but very poor power delivery capability. Supercap is often paralleled with that type of a battery. Lithium coin cell is a great example. Stores a good amount of energy, but it can't deliver that energy very, very quickly. So the supercap is used to serve the high current requirements of the applications. It's called peak load shaving, generally referred to as peak load shaving. And so the supercap serves the high power requirement. It's trickle charged by the coin cell generally, or it could be trickle charged by the solar cell. And the coin cell is there just as a backup technology. So that's one application. As peak load shaving allows you to enable some kind of lower expensive battery technology or use a smaller battery. Another application is a backup application. So you need to suppose you need to shut down the application and save memory or save something. The supercap can do that, and then the battery operates in the background for a longer duration time. So a typical application, by the way, for a supercap could be you need less than 15 seconds of energy. And whatever it is you're trying to accomplish with a supercap, if you can't get it done in 15 seconds, then most likely there's another technology that is a better fit. Not all the time, but supercap is generally used to higher current rates. So it's dumping its energy in 15 seconds, and then again it can recharge in 1 second. But there's a lot of content on our website that deals with how to parallel supercaps with batteries, and a lot of examples of it, and it's very common. It's commonly done. It's one of the main applications with supercaps.
Jeff covered that pretty well, so I don't think I have much else to add.
Okay, great. Thank you both so much. Another question here. What happens if I try running a supercap at, say, 105 or 125 Celsius? Do I rapidly lose capacity and or supercap lifetime? Any plans to try to extend the rated upper end operating temperature?
Jeff here. So the electrolyte boiling temperature is somewhere in the high 80s. So we do have prototypes of 105 degrees C supercaps, but the market really for that is too small, and the cost of them, whenever we say, look, we've got this 85 degrees C product, or we got this 105 degrees C product, but it costs a lot more, and it's very limited production. Almost always customers say, well, I prefer the 85 degree, the lower cost version, and I'll just stay with the 85 degrees C. So that's happened many times. But if a customer actually wanted 105 degrees C, we could make that by adding, tweaking the electrolyte recipe. So again, the boiling temperature of the electrolyte is somewhere in the high 80s. So once, you can go to excursions, short excursions that might be above 85 degrees C, but generally speaking, you can't expose the supercaps at over 85 degrees C for very long, or you start to change the the state of the electrolyte, and you ruin the you rapidly age the supercap if that were to happen.
Okay, Jeff, thank you so much for that great answer. We've got a couple more questions to get through here, gentlemen. So next one we're doing, can you show how to get to the page on your website that matches with page 23 of the presentation? So that is not the only question about that. So if you guys could just let people know how to find things on the site quickly, I think that would be helpful.
Sure. So if you go to the home page, and on the main menu, there's products. So I think it's the second menu selection on the menu bar. There's products. The drop-down would show prismatics and cylindricals. It's in the drop-down. You just click on that line that says cylindricals. So home page, main menu, look across the gray menu bar, and where it says products, you'll click products, and it'll drop down 4 or 5 different options, and I think it's the second or third option down that says cylindrical supercaps. And boom, should take you very, very close to this page, if not exactly this page.
Okay, great. Thank you so much for that answer. And for anyone that is asking questions about the website or where to find things, we will reach out to you following the webinar to help you find whatever it is that you need. All right, gentlemen, we have a couple of questions left today. Next one, is there literature that shows how long a charged supercap will retain its charge over time under no load condition? And then in parentheses, it's saying a pre-charged supercap shelf life.
I think we have an application note on that we could send you, and so it's dependent on a few things. There's a curve there. There's a curve that says, depending on which supercap it is, what temperature it's at, things like that. But yes, and we could send you that information, and I'll find your question and I'll get you that information.
Okay, thank you so much for that answer. We are getting close to the top of the hour, so we are going to take one more question today, and then we will wrap the webinar up. So if anybody has a last-minute question for our presenters, please enter it into the Q&A window and click Submit. Any questions from here on out, we will reach out to you following the webinar. All right, gentlemen, our last one for today is a supercap for a very low current sleep and low pulse load, a good fit to carry energy overnight from PV. Primarily lithium batteries available for backup. Looking to use PV to power up to 80%.
Sam, you want to?
Go ahead, Jeff. These questions are really great, and I think you're the one that needs to be answering them. I have no offense.
Okay. Sure. So supercap is great. So in terms of leakage current, you're talking about months, not days. So if you were to charge a supercap in the day and then hope that the energy was there at night, it absolutely would be. It would be there for days, and again, I can provide the curve that shows you what happens to that energy once the supercap is charged, and how long does a supercap retain the energy, and what rate does the current leak out of that supercap. But absolutely charged in the day and used at night, or within a couple of days, it's 100% of it's still there, and it's perfect. So it'd be a great application for a solar cell to charge a supercap during the day and use it the next day, or that later in the week or the next week. So it'd be a very ideal application.
Yeah, and I guess I could add a little bit to that. That typically that is one great use case of a supercap is maybe you don't need the device to last for a month if no light is available. Usually you get light available on a daily basis. So a lot of times your use case might be, I just need to make it through the night. And a SuperCap can provide that energy storage to make that difference, to make it to the next day, or provide a couple days of a gap where you might not necessarily need that larger storage capacity of even a small lithium polymer battery could last for months, and maybe that is just not needed for your use case. So a SuperCap could be a great option to kind of bridge the gap between the daily light exposure.
All right, Jeff and Sam, thank you both so much for that last answer. As I mentioned, we are going to wrap things up right now. I want to say a huge thank you to Sam and Jeff for great presentations and for answering all of our attendees' questions. So, gentlemen, thank you both.
Thank you, Katie.
Thank you, everyone. Jeff out.
All right, thank you guys both. And a huge thank you to our audience members for being part of this webinar event. Take care, and we will speak with you soon.